closer feel to it.
Yeah, it's got an almost improvisational tone.
This semester on Stat 201, prepare yourself for YouTube, because we're all zoomed out. Cahoots and special guests, Tiny Brian, Puppet Shark, Evil Moobot,
I am Moobot.
Morty the Rabbit, and more. Super Statistics Bros.
Hey everybody, how are we doing? I think I've got everything working. Are my earbuds playing? I don't hear the music on my earbuds. I don't know what it is. Let me disconnect, reconnect the earbuds. If you're in the chat, feel free to say hi. But I don't hear the music, and I'm wondering why. Let me connected mic, disconnect. We don't want just the microphone. Now I heard the boo boop, disconnect. I want to reconnect the AirPods again. Just weird things. Hey Elizabeth, good to see you here. I'm gonna start probably with some 320, then we'll hop into some 201. So I'm trying to get it so I can hear my sounds. AirPods not connected. AirPods connecting in. So I forgot the 2-factor. Let me send the push again. Oh, we got the boot. Let me hit the thing. Still not gonna hear music? That's a bummer when things don't work right? Hell, you're hearing the music probably, and I'm not. It's so weird. What is going on? Does it say connected? Connected audio. Oh, there's the music. We can hear it now. I hear it. Yeah, I couldn't hear it. It's for me, it was not playing. But I like to hear what you hear. So that way, if there's any like crazy noises, I'm like, what's that noise? We're gonna start with a little 320, then we're gonna hop to some 201. So there goes last night email. Okay. Important. How to do well on the tests. Join, click here. I am doing a quick advice. I will be giving some advice in office hours today on how I would create my sheets for help with the tests. Click here. Okay. They're gonna have to go to this timestamp later. Update it. All right. My advice on how to do well on the tests. Let me get some Word documents open. And then. Yeah. Okay. Almost there. Okay. Let's do this. Here we go to the main screen. Let's do it. Okay, if you're watching this in the future, we're talking about how to do well on the test for BAS 320. We'll start this section off with that right here. So 513 BAS 320 test advice. So on the test, you get one of two things. It depends which test you're doing. On the test, you either get an RMD file, or if you're doing the computational, you get an RMD file or an R file, or you are doing a front back sheet. So conceptual is going to be front back piece of paper with notes. That's the conceptual. The computational is going to be a .rmd or .r file. So these are the two things you can kind of have right here. And you can print, it's front, back, notes, one of those right there. Now let's go down to this right here, because I think the computational is tomorrow. I'm always afraid to say what's when, because yes, it is tomorrow, at least for my section. So here's the computational, and you can see it's tomorrow. Now with this right here, Dr. Petrie has posted how to do the mock midterm, to do a walkthrough of it, to see what you're gonna be doing. So go through this, check this out, know how to load it up, so when you get to class, you want to be able to load it up. Watch this video here posted for you on how to load it up and do it, and then load it up and do it so that you know how to do it. But here's what I want to point out. This study guide for the midterm It's one of the best study guides you will ever see. Has the rules for each of these right here, the computational versus the conceptual, on what you can have right here. You can have handwritten, typed, or whatever you want. So you can have that piece of paper I told you about. Only browser page allowed to be open is Canvas. So you have to have Canvas open at all times. Stream bitrate is doing weird. Sure, maybe let me fix that another time. Calculator, bring a calculator, and bring scratch sheet of paper right there. You can have one additional RMD file open while you're doing the exam. So basically have two things open, don't have anything else open. Only browser page open is Canvas and no notes. So very clearly what can be used right here. This is very clear on what you can use and what the requirements are for the exams with the first exam and the second exam. Now here's the important part. Down here, computational exam. 2 questions about evaluating mathematics. So what you can literally do, we'll ignore this update, go in here, ignore update, is you want to make your RMD file. So to make your RMD file, you would go to the plus and new R Markdown file. So hopefully you've done this by now. You want to have an R Markdown file for this. So I'm going to go here. I'm going to make my file real quick. 1 second right here. We're going to call this exam 1 help file. And here we are. So now I've created the exam 1 help file and I have this ready to go. So now when I go down to this, I'm just going to delete off all this nonsense that I don't want. And I'm going to start the first part. I'm going to call this evaluating equations. You can do like we did on your assignments, the double dollar signs, and you could do something like 2 plus 2, and this will make it appear right here so that you see 2 plus 2, and then you could throw in an R chunk below it such that you solve them out right here. You can add in different ones, and you could put in solving math, and there you go, solving math, and you can see you get the evaluating equations, solving math right there, and you could add in different equations down below this. I always forget how to do the LaTeX stuff. It's like backslash, curly bracket. Look at the assignments to see how to do this. Log, no. It's, you do the backslash, then you type in the function, and then you do this right here. And if I do like SQRT, it should make a square root. There it goes. So there's square root of 2 times, and then you can do backslash, it's gonna be backslash, frac. This is not stuff we do so much. 2 divided by 2, or, oh no, you do 2, and then you do the second one. There we go. So can we do quiz 8? Yes, Savannah, you bet. And this is, just want to do a quick segment here to help out 320 because they get a help sheet for their test. I want to state, like, you should write out equations right here. You should put the solves for these, like 2 plus 2 right here. You should put SQRT 2 times 2 divided by 2, and you can see the answer to this question because it's times 1 basically. And so you can put the solves for each one of these on the screen. And notice how what we're doing is we're just going back here, and you can see what you have to do: expressions raising to powers, exponentials, logs, and all that stuff right there. One question using the left arrow repeatedly to update the value of a variable. So watch this. Let's go over to ChatGPT or UTKverse, and let's say, write a question in R and give the answer for the following prompt. So we are asking ChatGPT, which is, we're using UTverse, to come up with something right here where we have to update repeatedly. Now, will it do it perfectly? Maybe. Will it not? Who knows? But we're going to get something similar. Declare a variable x and assign its initial value to be 10. Using the left arrow, update the value of x by adding 5 to its current value. Again, using the left arrow upper, now multiply the current value x by 3. Finally, subtract 2. So basically, you get the walkthrough right here of doing this. And then what we can do is we can take this R chunk right here. We're going to copy this R chunk. We're going to go over here and call this section updating value updating value. We go right here. We insert the R chunk and we drop in the code right here. And then we go back and we grab the code. We grab the solution right here. And if you notice, we are literally creating a huge cheat sheet that we can use, which is allowed. And there's all the information. And we go right here and we say updating value. And look, everything is nice and neat right here for us to go through and go through. So you have to make this. No, this is 320. This is 320. So I think unless you're no, this is 320. This is 320. They have 2 exams this week. So this is their exam right here with the computational stuff. This is 320. I can't want to make sure that's clear. So they have all these questions right here. And look, you could go down further to, and probably doesn't know associate. One question that requires you to sort a data frame. There's so many easy ways to do this, because this question right here, sorting a data frame, is very cumbersome using base R functions. So if you get down to the sorting a data frame, if you get down to sorting a data frame and you know how to do it and you've done it before, so you could say, using the MTCAR dataset, sort the data frame by miles per gallon and CYL. So put them in decreasing order. It should be first sorted by MPG. Okay. So what you would do right here is you have the MTCARs data set, and there it is. Now we're going to load library dplyr, which allows us to manipulate data. And with library dplyr, we're going to go right here. And I don't know why my tools, well, fine. This one's using it below. We're going to go here and go to MTCARs. We're going to do a pipe, which is Control-Shift-M, or percent greater than percent. Then we're going to go into a range, which is the dplyr function. We're going to range by, you can do both of them right here, or we could just do it step by step. We're going to go decrease descending order MPG, and that'll do it in descending order of MPG. You can see it right there. And can we add another argument? Let's see what happens if we do this. And it might have done it. Nope, didn't do it yet. Okay, let's go here and do another pipe and arrange and put in the cylinder now. Try to arrange it again. And now it looks to have done it. Yeah. And just depends, like, we usually don't go this complex, but if you notice right here, it's kind of maybe needs to be put in reverse order depending on how we want it, by MPG, and put them, it should be sorted by MPG first. So I guess I'm thinking this makes sense here. Might make more, just the way it's worded. I don't even think we do we might do double sort, but this has MPG going down and then cylinder. So what you'd probably maybe want, or actually maybe it was doing it first that way. Let me look at this again right here. Yeah, I think this is it. Yeah, because the reason cylinder changes is because it constantly goes down by MPG, and then cylinder is at the end. So you see this right here, the 21.4 has the higher cylinder first, and so when there's a tie, you get the higher cylinder. So it'll make sure, so this is correct. So I was right to do it this way first. It's interesting. Yeah, so this is the right way to do it, or at least the way I wanted it, by saying it should be sorted by MPG first, and then cylinder within, in case there's ties, the cylinder would break the tie and choose the sort order based on that. So a lot quicker than using the order way. So if you look, we just did this one right here, sort a data frame. So if you go right here, sorting a data frame, that one's now been done, and you have an example. You could do others. So you could say example 1 right here. And then if you go in and you do another example, you could say like, use base R methods. So if you had to use base R methods to do the sort, which is not a bad thing to know either, you could call this example 2. Once again, you can grab these from your notes. You can grab these from examples in class. You can grab these from the homework. You can grab these from the solutions. You know, the more examples you have of doing this, you don't have to chat GPT everything. You don't have to come up with your own examples. Grab them from what you've been doing, construct this, especially if you start early, you can just keep adding them and look at what we have, because now we can do this with base R functions, where it's a little trickier. I've never used the order function twice on this. So we want to go to empty cars, we want to order the rows. So we're going to go to order on the rows of the empty cars data frame, miles per gallon. That orders it based on miles per gallon. And I guess we could overwrite, we could call this sorted empty cars 1, and that'll create that sorted data frame. And now we go here, and probably if we go here to CYL, and let's grab this. Once again, we're just showing how to practice, and you get your speed up by doing this. We're gonna store 2 right there to make a new data frame, and we're doing a right arrow because we can store to the right. And let's take a look at what we got, see if it's in the right order. Nope, it's got that other thing. So yeah, I wouldn't love this. We would maybe show you something of what it should look like. So there's empty cars. Oh, and then we have to take the sorted data frame. And now we're using the sorted. Okay, let's see if this looks correct. Oh, and we have to do decreasing equals true. The descending. Oh. There it is, decreasing equals true. Hey, Emma, so yeah, are you 201 or 320? We are currently talking about the 320 test. We're about to do some 201 after. Talking about the both 320 tests coming up right here. And I think we've done it. We have now achieved the same goal with base R codes. And you could do a check right here. You could go identical, which sees if 2 things are identical, sorted 1 with sorted 2, and they are identical, showing we've done it correctly. If we had it, if they weren't identical, it would tell us false. But by doing this method right here, we've achieved the same goal. We have identical. So we use base R functions. And that's why I don't love the base R functions, because dplyr makes it easier to say, you know, do this right here. Put it in descending order of miles per gallon and descending orders of cylinders. A little bit easier. Maybe I could have made the code cleaner for the base functions. But this is how to get ready for the computational, is to have all your examples right here. Like when you go to, oh, how do I sort a data frame? Go right here, and then here's my examples. So this is the key thing. Make your RMD file, have it be a walkthrough for you. Now, when it comes to the conceptual, which is on Wednesday, Thursday, you've got a little more time to prepare for. And I keep saying, make these things, like over the weekend, make this thing. Go to the questions. And here are the questions for the conceptual. The conceptual literally says choosing Y and X. So if you have something like, so this is good for 201. So 201, if you're here, try to answer this. I'll leave a pause on it. If we are trying to predict, let's say, somebody's burned calories from miles run, well, darn it, from miles run, what would be X and Y? I almost can't help but lead more things into it. You have burned calories and miles run. So what do you think would be the Y and the X? Because this is what these questions would go over, is which one makes more sense to be the response or predicted variable, and which one would be more sense, which should be more sense to be the explanatory variable. Some things like height and weight are interchangeable, but I would say calories burned and miles run have an XY relationship most people would agree with. When we talk about which one do we predict and which one explains it. So you think about kind of almost an antecedent, the thing that comes before, antecedent, and consequent, the thing that comes after, or like during it. So we'd probably think there's this sort of XY relationship between miles run and calories burned. So this is also a 201 question, like what is the explanatory, what is the response variable? Let's go down here. I love when people pick random things. So let's do this. Watch this. We're going to use code right now to pick, let's go to sample. So people don't think I'm biased, so I can do one right here. Let's go to sample letters, and we're going to sample one letter, and we are doing letter U. So we just picked a random one. Identify when making a prediction what would require extrapolation. So let's go right here, and let's go to ChatGPT and watch this. Explain to me 2 steps I can perform to answer the following question. So we're asking ChatGPT to explain to us 2 steps we can perform, and drop some questions in the chat. We're about to do some 201. So quiz 8, we might start doing. Understand your data range. That's a really good thing right there. So it says understand your data range, which is the range of the X's. This should definitely talk about the range of the X's. And it's talking more about a time series predicting sales. Check your model assumptions. Really, this is way more detail than I would have said. In only 30 characters, explain when we would extrapolate. Explain the following. So I'm trying to limit it. And beyond data range, extrapolate. That's pretty good. Elaborate on that last idea with 2 more sentences. Like, that's too small. So elaborate on that last idea with 2 more sentences. Like, beyond the data range, extrapolate. That's pretty much what it is. And by range, it means range of the x's. When you're asked to predict value that falls outside the range of your existing data, so its predictions are based on x's, this is called extrapolations. Essentially, an estimate beyond the known values based on the assumptions that current... Yeah, so you'd have to understand what's being said right here. So I do kind of like this, but if you go down here and you go to question U, and you say, step 1, do I have x's where I am asked to predict y? And we go here to yes, not extrapolating, and no. And you know what's really funny? This is 201. So we have question U right now. If you want to save space, you could put it next to it, because you want to keep as much space as you can without making the text too tiny. But you could try to put it next to it right here. And we are making a pro cheat sheet for us. It's not really a cheat sheet, it's our notes sheet. But does this make sense right here? We have question U, and we don't want to use that line right there. Look at that. That is about as nice and neat. Do I have x's where I'm asking to predict y? X values. We're predicting y. So you think about how to make these things concise. Do I have x values where predicting y? Yes, that is not an extrapolation. No, that is an extrapolation. So you want to make these like step-by-step things on how to do this, because then you can look at a graphic, and let's go grab a scatter plot, and then we're going to go to some 201. So 201, I need some questions. Maybe we'll do a homework 8. This is actually your guys' assignment. And so where would we have extrapolation here? When would we be extrapolating this model? When would we be extrapolating this model? Who knows? This is your guys' work. So where would you be extrapolating this model? See if you can answer it. Where would you be extrapolating this model? See if anyone, 100 points. Your 201, this is something you should know. This is when you have a deeper understanding, when you can answer your own questions. Great job, Owen, right there. 15 and 35 outside of those ranges, that is extrapolation. But Owen and Hohen, we said 100 points right here. When would you be extrapolating this model? Now be careful. This one's a bit trickier because it has some extrapolation more within. And I really like this one. I found this graphic over here really quickly. So there's some points of extrapolation. So the more data we have around the x's, the less of an extrapolation we are doing. So at a point of an x, there is no extrapolation. We have an idea of where that model is at. And so we understand ish where the model is at here. And also there's a bit of a either outlier or nonlinear relationship to this. And so the point is, within this region, I would say around 8, we are extrapolating a bit because we do not understand what the model is doing, because we don't have x's in that range. So below here is extrapolation, beyond here is extrapolation, and then we also have a big question mark inside of here because we don't have data within that range. Does that make sense, Owen? You have to be careful because extrapolation can happen within a model. Like if you have data points that look like this right here, a lot of times when doing experiments, you want to get a middle point, because if the data goes up here, the model goes like this. If the data goes down here, the model goes like this. If the data is here, the model goes like this. So we use middle points in experiments. Yeah, it looks like 0, 12, 8 are points at which we are extrapolating. And this goes to how we do experiments sometimes, is you create a middle point to check for linearity, because you don't know if your model's like doing a non-linear pattern, because in the middle of the data, you don't know, like you don't know what the model's doing. You'd have to create like bands or something around it. And also the bands might not be tight because there is no data at the middle, even though the middle is where we have the most certainty usually. So usually the best thing to do is have data around the middle of your model to tell us if it's going to go up or down or stay right there. So does that make sense, Owen? Really good work, really good practice. Thank you for swinging by. Let's do some chapter 8. Okay, drop some questions in the chat. I think we might be doing the homework, maybe. If no one says anything, we'll hop to the homework, because that's one thing we can do the full thing of. And those topics, Alexander, great job right there. So remember, make the cheat sheet and have examples and have step-by-step how to check extrapolation. Do this. Like, have your steps. When you get to the question, you're like, oh, how do I check extrapolation? I look to see if there's values of x's around the point at which we're making predictions. If there is, we're not extrapolation. If there's not, we are extrapolating. So have each one of those listed with a methodology to use to solve each question. Use your cheat sheet. You're welcome, Owen. Good luck on the test. Remember, all the questions are listed, so think about how you'll solve them. It'll help you prepare for the test too, because then you'll be like, how do I do this? When do we learn this? What am I doing? What am I doing? How we doing on the assignments? Let's look. We got a due date coming up tomorrow. Oh, and the grades are not good on it right now. You send out a reminder to 201 and say, because we did a lot of this last class, and I'll say like, start now. We're gonna send out a reminder and just be like, chapter 7 is tough, start now. Okay, let me send a reminder. We did a lot of it. We did some of the toughest questions. Send this, and we're gonna do some homework, but put those questions in the chat. Okay. Trying to figure out what kind of functions of code I should have on the R markdown file. I want enough to help me out, but if I have too much, I'll get lost. So Jaden, big thing right here, big thing. What you want is go in order. So do you see right here, this is what you want. You want to have your RMD file, and then you can go in order of the questions, like evaluating equations. So right here with this function, check out the start of the office hours right here, Jaden, really good questions. Notice how I have evaluating equations, and go over to the assignment right here. And if you go to 2 questions about mathematical expressions, that's the first question right there. So you could even put right here 2 questions about mathematical expressions, and so you could do this. That makes it really long, but evaluating equations, 2 questions about mathematical expressions. So you can keep track of where you're at doing the file, and then updating a value. So here's the one question right here. So then while you're doing this, you can see where you're at, and you just keep this. Yeah. So have this right here, so that way when you're doing it, you can click through it and be like, so you could even put right here Q1/Q2, and now you go here to Q3, because I think we go in order. I think Petrie just did these in order, so don't quote me on that, but it's like, if you are doing this right here, you'll have a very good organized file. It just depends on how much you want, and then you could just put examples right here. You could call this example 1 within this. You can't knit it if you do this, but because it'll get mad at, but we're not going to knit this, so you could call it example 1. But does this make sense, Jaden, right here? This is my biggest tips for this, is to have this well organized file that when you're doing this, you can just click here and go to your evaluating expressions, and then put all the examples you can in here. You can put them in different chunks or whatever, but if you go down to sorting a data frame, which is way later, you can see your examples on how to sort a data frame and use the code. So, and if it goes in order, you just keep just scrolling down while doing it. So big thing there, big thing. I don't think there's anything bad about having a big file. It's just like have multiple files, and then just have it very organized. So you can just click and go to that spot. Yay! Okay. And now reminders. You're welcome, Jaden. Keep up the good work. You got this, man. Okay, we're gonna do some chapter 8 homework. The number one thing to do is to start early. It's the earlier you start making your cheat sheets, the earlier you start on assignments, the easier they are, because these assignments can be tough. And then if you just have more time to say, how do I do this? Then someone comes in and say, oh, just do this. And you say, oh my gosh, roller coaster, we might have done it. We could do it again. You're here, so we get to do it. I don't think we did. That was a little bit tricky. So let's do the roller coaster question. Thank you, Emma, right there. You're here, so you get the question, and drop other questions if you want. We're gonna do the roller coaster question since you've asked. Good question. Thank you so much. When you're here, you dictate what we do. Unless I choose one thing that at the start I'm like, oh, we're gonna do this one thing because they have a test tomorrow, so I wanted to make sure I put this in the video. And we already saw a few people swinging by to ask questions, so good to go. Okay, you're welcome, Emma. Yay! Let's go check it out. Roller coaster question. This one's, it's towards the end. Watch this. It's number 16, I bet. I've been doing this too much. Okay, let me put this in the notes. It's not one of my favorite questions. It's got some good parts. We'll talk about the learning objectives from it. Roller coaster, a data set. Dataset on. Roller coasters. Okay, here we go. So in this data set, you're dealing with roller coasters and they're looking at the drop and how long the ride lasts. So what you want to think about is if you had this little tiny roller coaster, not bad. Would this little tiny roller coaster last a long time if you were on this roller coaster right here like this? This is you on the roller coaster. And would this roller coaster last a long time? Would that roller coaster last, the top roller coaster A, last a long time? No, it wouldn't last a long time. So it's counterintuitive because I do agree if you drop really fast, the roller coaster would go faster. But this roller coaster down, this one right here, you just be like, woo, and it would stop. The roller coaster down low is going to have a, you're going to drop and go, wah, and maybe even go around a track over here. We'll say it goes around this and it swings back over here to the end. So this roller coaster has a huge drop, then you go around, and so this roller coaster is going to last like a minute and a half, 2 minutes. This one's going to last 3 seconds. So now we're talking about the units, which is not my favorite part of this problem. We are trying to predict how long your roller coaster will last, which is duration. This is like 320 a moment ago, where we're trying to say what is the X, what is the Y. The predictor, actually, and I hate that they call it the predictor. I don't like calling it the predictor. I like calling it the explanatory variable. And we are using the drop to explain in units of feet the response of duration. Predictor is another name for explanatory, and I don't like the name predictor because if you call the X the predictor, you should call the Y the what-id. Think of my sentence here for 100 points. If X is called the predictor, Y should be called the what-id. So think of my sentence. If you're calling X the predictor, you should call the Y the what-id. If you're calling X the predictor, you should call Y the what-id. Makes more sense. Because then I'm like, don't call it the response then. I would say the response is what we talk about, the predicted, yeah. So I don't like, it's like, if you want to call it the predictor, cool. Call Y the predicted, because we're going to predict Y from the predictor. I prefer to call it the explanatory variable, because then X does the explaining on Y, the thing we talk about, the response, something happens. Right here, the units of the drop is in, or the units of the duration is in seconds. The slope is going to be like, this is where I might get it wrong, because I'm like, okay, it's X by Y, like Y per X? Y per X, right? So it would be how many seconds long it goes per foot. Like for each additional foot, there's more seconds to the ride. And the slope is probably positive, even though we could disagree, like bigger drop might make the ride quicker. They're going for a longer drop, goes for a longer ride, and this is where I have my qualms. Because coasters with bigger drops probably provide longer rides. You'd have to go with that, but if you went negative, you'd have to go here, and that should be right. Got 100. Not one of my favorite questions. The big thing on this one is maybe what is your X, what is your Y? Understanding that relationship. Units are important for interpretation. So you have to think about your slope here. For each additional foot that drops, we would expect the duration to increase by 0.2 seconds. So for each additional foot the ride drops, we expect the duration to increase by 0.2 seconds. And also if the ride has a drop of 0, which is meaningless because then there'd be no ride, it would have -3. And I do want to point this out. So we're just doing one last bit, and let's do another one. Manager at a bookstore, sure, you bet. And what do you need to be able to do with an equation like this? What do you need to be able to do with an equation like this? What do you need to be able to do? Interpret it. So this is your Y, variable of interest, technically predicted Y. So we put a little hat over it. Can you tell me which days and times you are alive? Yeah, Monday, Wednesday, 10 to noon. And then we have some additional times elsewise. Good to see you here, Rachel. 30 some points. Monday, Wednesday, and then sometimes random other times. But till noon today, until noon Wednesday from 10. And so this quantity right here is known as B0 plus, you're welcome, B1x. And then we also do cahoots. So stay tuned for those. And so when we do this, the slope coefficient is y hat is predicted. Yep, and y bar is mean. Great job, Andrew. Good comments and answers. And so what you would say here is for each additional 1 unit increase in feet, we expect the duration to increase by 0.2 seconds. When feet is drop is equal to 0, which is feet, drop, I should put drop right there. We expect the ride to last -20 seconds. This is impossible because a roller coaster with 0 drop would have no duration, and also you can't have negative duration. Does that make sense? When x is equal to 0, we expect y to equal b0. For each 1 unit increase in x, we expect y to increase by b1 or decrease if it's negative. There are 12 points on your test. Now let me ask you one last thing right here. If r squared is equal to 0.80, what does this mean? Try to write it in the chat, then we're going to do the next question. I keep doing test question related questions for you right here. So hopefully watch these parts of the video because this is a test question thing. What does the r squared mean? So, well, it's not duration. Kind of, it depends. The two steps to get correlation are 1, to square root it. So square root, and then 2, check direction. So, but, oh, nice job, Rachel. Yep, and then a little more context. Rachel, 100 points right there. Rachel has basically said it, 80%. And so Rachel, give a little more context, 100 points right there. So Rachel, a little more context. This is good practice. This is test practice. This is 4 points. You got to put in the context, though, to get the full 4 points. That might be 2-ish points because you're missing the context. Ashisha, great. Thank you so much. And thank you for being here. If you have stats questions, let us know. We appreciate it. I've got some friends over in India. Well, he's over in Germany right now, but he's from India, born and raised, and he's over in Germany right now doing a study abroad. So I get to learn a lot about like other cultures and stuff, and really nice. So shout outs to Didi if you're watching this. Shout outs to you. So he goes by Didi. So shout outs to you. We need a little more context right here. Is Mubot not awake? This whole time, Mubot hasn't been awake. So Rachel, just a little more context, and we're going to do the bookstore manager question. Just a little more context. You have to look at the X and the Y and put them in there. And this is practice for the test. We're so close. The Y right over there is duration, and the X is drop. So I'll always look to the equation for the, and I've got listed below. You see how we have right here the duration is the Y and the X is the drop. So you're right there. You're right there. You got it. This is just practice, and then we're gonna do the manager at the bookstore question. Right there. Look at this. This is too funny. There it is in the video. Blank % of the variation Y is explained by the variation in X. So when we do this right here, 80% of the variation in duration is split. Yeah, Rachel, that's it. That is it. That is how you do it. You literally just take the X and the Y, like this one right here. You would say, whatever R squared is, 60% of the variation in Saturday text is explained by the variation in Wednesday text. You 100% did it. And then just make sure to say 80% of the variation. Make sure to say variation right there. So look at how all you're doing, and I'm going to highlight what you wrote. You're doing perfect right here, because all you have to do is plug in your X and your Y. So it's plug in R squared, plug in X, plug in Y. And I highly suggest checking out these videos. If you look at these videos, I give you the interpretations. We're talking about residual plots. That was a cool transition. And when X is equal to 0, we expect Y to equal B0. Check out these videos right here. Is there any evidence that an animal's gestation period? Oh, is that chapter 8? We'll do that here coming up soon. So make sure to check out these videos and see how we do it. Oh man, it's back when I put the calculator on the screen. I got to get that app again. You can see we're talking about residuals right here and a negative residual. Just came from your video. That's how I got. Nice job. Okay, let's do the manager to bookstore. Then we'll do gestation coming up next. Roller coaster questions. Okay, manager to bookstore here. Nope. Turn around here. Oh my gosh. This drives. Manager to bookstore. We got 2 manager to bookstore questions. And so let's do both version and then animal gestation periods. Okay, and do remember, these extra bits right here are the ones that really matter because I know what's on the test. So I want to hone us in on being able to do this. The manager of a bookstore. Okay. So first off, it wants to find the slope and the intercept. The slope is B1, the intercept is B0, and we get data. Now doing this by hand is not fun. So don't do it by hand, use jump. So I'm gonna get jump up and going right here. And we're gonna show how to do it in jump. So jump makes this a billion times easier. So you want in jump to go to, we'll zoom in, file, new, oh my gosh, what am I doing? File, new, data table. It's going off the screen. File, new, data table, which I just found out recently is this button right here. There you go, new data table. The little button right there makes a new data table. Clicked it by accident, got a new data table. Now inside of your data, you want to click it first, then click this, then copy to clipboard, then hit Control-C on a PC or Command-C on a Mac. Let's do those steps again. Click the data sheet, click the little window, click copy to clipboard, click Control-C or Command-C. Notice how there's column names. Those are column names. Now, when you're back inside of your new data sheet, first off, make sure you've not clicked inside of it. A lot of people click inside of it. If you did that, just start a new one. Now, go to Edit, Paste with column names, because there was column names. And there you go. If it turned out red, you've done it improperly, and this is not correct. So right here, you see the not correct version because the column names went into the first row. Just restart, new data sheet, paste with column names. And here you see the correct version on the far side. So make sure it looks blue. Blue means quantitative variable type inside of jump. So now that you have the data there the correct way, we're going to go to Analyze, Fit Y by X. Analyze Fit Y by X is the bivariate way to analyze data, which means 2 variables are going to be analyzed. We have X, the explanatory, and Y, the response of why something is happening. So the bookstore is probably wondering, well, maybe our people working, like maybe the workers we have, explains why we get so much in sales. You can drag, drop, or click, but maybe the number of workers explains why we get so much in sales. When you click OK, you get a scatter plot. A scatter plot is the visualization of 2 quantitative variables, and clicking the red arrow gives additional options like the fit line to add the trend line to the data, known as the line of best fit. It is the best fit line because it minimizes the sums of squared error, which means it tries to make as little error as possible. And we measure this by squaring the error because some errors are positive, some errors are negative. Summing the errors gets you 0, but squaring them makes them all positive. If you sum them, that's a quantity of error. So we fit the line right here, and there it is. You can actually see the sum of the squared error. Under the ANOVA down here, there's a total of 258 sums of squared error. The line reduces it by 251, but we don't do this in Stat 201. That's an ANOVA, analysis of variance, different day, different topic. But the line does really good. And what do we mean by that? If you look at the line, it kind of gets super duper close to all the points. Now the equation of the line is going to be seen right below this. And the equation of the line is right here. I'm going to make it look easier. we're just going to write out sales. We're going to put this to 2 decimal places. And then we're just going to click away from the question and maybe lose it. Let's hope we have the same. Didn't change the data, did it? Oh, it's going to be nice if it changed my data on me. We'll find out the hard way. And we'll say workers. Now here is where I ask you, if you're in the chat, can you interpret all 3 values? Can you interpret the intercept? Can you interpret the slope? And can you interpret the R squared? Take a moment, 100 points each. This is test practice. Remember, the intercept is when x is equal to 0, we expect y to equal b0. The slope is, for each 1 unit increase in x, we expect y to increase or decrease by b1 on average. The R squared is blank percent of the variation in y is explained by the variation in x. So can you do it? Try it in the chat. You will be typing these out. So try typing it out. If you're watching this in the future, try writing it down. Try typing it out. Go to the sheet next to you. It'll answer the questions we're about to do on Mike Pearson. So we'll look to the answers you give. We'll give it this full song. We'll go full song right here, and then we'll look at the answers. But this is the practice you need, because clicking these buttons will not get you the practice. Clicking the buttons and seeing what I click, it's good. You get some points. But you get the test, you say, I don't know what to write because I never wrote it down. So if you want to know what to write for the test, try writing it now. So listen again, I'll highlight the numbers as I am saying, or highlight the values as I'm saying what would go in the spots. For the intercept, when x is equal to 0, we expect y to equal b0. So all you have to do is plug in the values right there. For the slope, for each 1 unit increase in x, we expect y to increase by b1 on average. All you have to do is try writing it down and put in the values. We'll do it one more time around here. You ready? Try writing it out. There we go. When x is equal to 0, we expect y to equal b0 on average. For each 1 unit increase in x, we expect, correct, Elizabeth, but you gotta do the full interpretation on the test. That'll get you like a half a point. That'll get you half a point. So on the test, you have to write the full interpretation, which would be for that, when x is equal, or excuse me, for each, but you have to write the full interpretations, Emma. It has to be a full interpretation on the test. It has to be full sentences. But yep, these are the values. So you have to get the full sentences. Good work. This is what I'm training people for. Because you get to the test, when there are 0 workers, we would expect Maya, great job right there. Maya said it right there. When workers are 0, and this doesn't make sense, right? Because if no one's working, how do we make money? And it is technically in thousands of dollars. We would expect sales in thousands of dollars. Sales, it's fine. When there are 0 workers, we'd expect sales in thousands of dollars to be 8.61, which doesn't make sense because no one's working. So how about the slope? Ready for the slope again? For each 1 unit increase in x, we expect y to increase, because it's positive, by b1. So try this out, and good work, Maya, right there. We're working out, we're making sure we got this. As I blur out of existence. So what do we have? For each 1 unit increase in x, we expect y to increase by b1 on average. Try saying it, try writing it. Then we got to do the R squared. Because then we can just answer every question like this. What do we got? Give it a shot. Don't worry about being wrong. Because on the test, you have to write the full thing. For each 1 unit increase in workers, we expect sales. Nice job, Maya. Good work. That's exactly it, Maya. And so now, what is the R squared? You're just one step away. This is the practice we need right here. So what is the R squared? R squared is blank percent of the variation. So R squared percent of the variation times it by 100 in y is explained by the variation in x. So R squared times 100% of the variation in y is explained by the variation in x. Try writing these down. People get to the test, they say, I have no idea what to write for these. And I'm like, we have to practice it. Every time we do one of these, we have to do it on our own. 12 points on the test right here. 12 points on the test. So blank R squared times 100% of the variation, 97.46% of the variation in sales in thousands of dollars explained by the variation of workers. Maya, you didn't even put a question mark. You're like, I know this, I got this. Easy answers. We're gonna do this really quick right here to confirm I have the answers, because I did restart the question by accident. So I'm just quickly going in here, restarting it, and analyzing fit y by x, because I'm worried that somehow I changed it by restarting it. And the answer is 8.61, 88.89. Nope. I'll say 0.89. The slope is going to be, it means on average, an increase of salespeople working is approximately increase of total sales. No. So it means that on average, the number of salespeople working is approximately, what? There it is. It means that on average, an additional increase of B1 in sales is associated for each additional. So they put each additional person working is expected to increase our sales by this amount. Don't love that interpretation. And then the other value is 8.61. And this is, it would mean on average. So it would mean that on average, the total sales would equal, nope. With zero, there we go. With zero salespeople working, it does not make sense because it's unlikely any sales would be made if zero salespeople are working. Write out the equation. So it's literally just taking the values we have of B0 and B1, plugging them into the equation. Predict if 14 people are working. So we go to our equation right here, and we just plug in 14 for x. 14 times 0.89 plus 8.61, and there we have it. And you have to turn this into thousands of dollars, so it moves over. Now, here's an important thing. It says this is the predicted. So in notation, what is predicted? So in notation, predicted is what in notation? Let's circle some things and highlight some things here. This is the predicted value. This is the actual value, and it wants the residual. This is the x. So this is x. So what is the predicted in notation? What is the actual in notation? And what is residual in notation? Does anyone know any of these right here? Have these written down. Put them in your notes for chapter 7. When it says predicted, when it says actual, when it says residual, what are those in notation? This is the important things right here. So what are those? Make some spots where we can enter these in. Knowing the notation. How'd you get the predicted? Plug in x into the equation. So if you go to the equation right here, because it says if 14 people are working, so you go to the equation right here and you plug in 14 for x. So with the equation right here to get the predicted sales, you go right here and you take this value right here and plug in 14 and you solve the equation. Does that make sense? Plug 14 into x and you can get the predicted sales for 14 people working. So what are these in notation? Nice job. We predict. Great job. Good interpretations. So what is the notation for these, though? What are the notations? What are the notations for the predicted, for the residual, for the actual? What are the notations for these? What is any of the notation for any of these? Predicted, actual, residual. Write down these equations, know them. You do get this equation, but you should know what it means. What are these values? What are they in notation? Any ideas on these values? Residual, great job, Alexander. Residual equals actual minus predicted. So residual equals actual minus predicted. And when we change it back to notation, residual is E and actual is Y and predicted is Y hat. So the predicted is the Y hat value. The actual is the Y and this is the E. So we go right here and we start plugging in values. Predicted is 210710. or that rounds down. Be careful. I don't know how I got that 4 in there. Oh, I think I just typed an extra 4. That extra 4 is an error because if we rewind the tape, there was not a 4 in that. And here's the calculation right there. So moving the decimals over, there is not a 4. Somehow I accidentally typed a 4. Predicted is y hat. Great job, Rachel, right there. The predicted is the y hat. And you can even see it in the equation where it shows right here, the y hat value is predicted sales. So it's even saying predicted sales. So that is the y hat, because this is the y value, and on the other side you have the x. So now we plug in the values, and the actual is here, and all we have to do is subtract these values to get 930. And what this means is the residual is positive because the actual is higher than the predicted. So the actual value was higher than the prediction, which comes from the line. So we get a positive residual of 930. Really good question right there. A few steps to it. So a lot of people get stuck on a multi-step question. We also answered the question of, have we underestimated or overestimated the price? So what do you think here? Did we under or overestimate the price? So look at my graphic, which I'm blocking. Did we underestimate the price or overestimate? The dot is the actual. So did we underestimate it with our model or overestimate it? We underestimate it because the model is underneath it. The model is the line. The line makes anything on the line is a prediction, and all the dots are the actuals. Like dots below would be overestimated by the model, and dots above would be underestimated by the model. So the model is below us, and we have underestimated. We should get everything right. Woohoo! It's a really good question. That is very much a good question right here. R squared. There's R. To get R squared from R, you just square it. What is this not? And times it by 100 to interpret it. So what is R squared not? We say this in our class. So percent of variation in sales. So is it 2 decimals? 1 decimal. Is the percent of variation in sales that can be accounted for with the regression model on sales on number of sales per work. That should be right. There we go. It's not correlation. Great job, Rachel. You got all the answers. Nice job. It's not correlation. It's percent of variation of y explained by the variation in x. It can be computed from correlation. Like if I squared 2, it's no longer 2, it's 4. R squared is not correlation. It can be derived from correlation. Great work, Rachel. So really good stuff. We're going to do the gestation one next. Really good review of these concepts. That last question is 50% of the chapter. It's a lot of it. So if you did that last question with us right there, good work. Okay, and thank you for everyone for all those interpretations. I cannot state this enough, that writing your interpretations is key. People get to the test and they say, I have no idea what to write. And I'm like, no, we did it so many times. And I swear if I look back at the people who write the interpretations when they're here watching, they can do it like that. Because we'll practice it like lots. We'll practice it again tomorrow. So every time we get this chance to practice interpretations, just take a moment and write them down. Even if you get them wrong, don't worry. It's just practice. So you only get better by practicing. We found the animal gestation one right here. Let's go take a look. This is one of the ones I like. Some questions are better than others. Can't say all questions are amazing. Then what would that mean? Stat 201, chapter 8 quiz. Is there any evidence that animals gestation? Okay. Let's go do it. Gestation is going to be how long they are pregnant for, where life expectancy is how long they live for. We got the humans over here. So the humans are over here at how long? I guess that's how long 9 months is, right? 9 times 30 is about 270. So if you think about what this is showing right here, humans are definitely a what in this data set. If you look at humans, where the pattern for the rest of the data goes like this, humans are down here. So we'd have a pretty big negative residual, which means the model would overestimate how long we'd be pregnant for. The model says a human should be pregnant for something like 2 years. It'd be crazy. Like a lot of time. So humans are a what right here? Humans are definitely a what in this model. So you can look at the rest of the data here. You can look at humans, and we yikes, I know, right? So humans are a ridiculous outlier. And so they're saying, like, what would happen? Great job, Maya, right there. So we say QQ straight enough, no outliers. You don't really just want to remove data needlessly, but you could just say, like, let's not talk about humans. Let's talk about animals that are not humans. Okay, we'll do that. We'll do that. For the data, this is the correlation. Do you think this association would be stronger if we removed humans? So what you want to do for these ideas is look at the data with humans and then look at the data without humans and notice how it's tighter. Strength is how tight the points are around the form, and humans are pulling out the density ellipse, like how dense it is within an ellipse. Since it's tighter around the line, it would be stronger, and slope and correlation would increase. It's easier to match a line through fewer data points, true, but it's stronger. It has nothing to do with it. Can remove humans? Sure, let's just not talk about humans. You can if you want. You can always remove data, but you should have good reasons. Saying we're going to restrict the data to non-humans is a good idea. Now, what I like right here is they give you the coefficients. And so in notation, what have they given you over here? Well, obviously, r squared is r squared. But what are these values down below? R squared is obviously r squared. What is this? What is this? So help me out right here. Oop, don't want to go there with that. Actually, that doesn't even need anything. There we go. What are these things? Tell me what these things are. Can you tell me any of this notation? Good important equation, no. Life expectancy, actually life expectancy is X. Good question right there, Maya. An answer, Rachel and Maya. Life expectancy is X. Does that make sense? Because it's on the X axis. It might make sense to predict life expectancy. That's kind of a thing you'd expect to predict, but they were predicting gestation. I do agree it makes sense for predicting life expectancy, but they were predicting gestation because that's on the I love R squared. RotoWave, good to see you here. 100 points, RotoWave in the chat. R squared is an amazing concept that we do love. RotoWave, swing by. Hope you're doing well this semester. So, yep, so what we have right here is life expectancy is the X variable. And so this is what we put in X right here. The coefficient of X is, I think, and Maya said it, I think. Maya is correct. And this is B1, this is B0, this is Y hat. So that's predicted gestation right here is equal to 90.85. We'll just round it, and 12.9. Does that make sense how we can pair this up? Try writing down these equations and think about how you would solve it out right here, but you should be able to take the information that this is with the X variable right there, so that's the coefficient of the X. They're calling it a constant. Some output might just even leave this blank. Other output might say intercept right here, but that is what we have right there for the model. Yeah, swing by any day. I use RotoWave, of course. R squared is huge. RotoWave, more points in the chat. So yeah, R squared is a big important concept. The association, this is just once, it's if it's strong, weak, or moderate. So you want to think how tightly clustered are these points to say how strong it is. So what do you think? Is this a tight, like strong, moderate, weak? What are your thoughts on this? Give me tight, weak, moderate, strong, something to describe it. Then we're going to look at their answers. What do you think of the tightness of this around the linear form? What are your thoughts on that? That's what it's asking you to analyze right there. We're going to look at their answers in a moment. Always think up your answers before looking at their answers. Is moderate? I'd say moderate, moderate, strong. It's definitely not weak. That's also positive. So the association is it perfect? No. And think about this. We said moderate, and I said moderate is strong. It's not perfect. That would mean every point's on the line. So moderate, strong is the way to go. Interpretation of the slope, we have to know the coefficient of the slope, which is 90.84. So on average, excuse me, this is the slope. and it wants to 2 decimals, so that's going to be 12.9, and it's an increase. And once again, I'm going to do this for you so we can do some more questions, put more questions in the chat. For each additional year in life expectancy, we expect the gestation period of an animal to increase by 12.9 on average. And look right there, it's literally almost exactly what I said, but for each 1 unit increase in X, we expect Y to increase by B1 on average. So if you look at their interpretation, try doing yours. For each 1 unit increase, or for each additional year in life expectancy, we expect the gestation period of an animal to increase by 12.9 days on average, because that's what gestation's in. A certain mammal has a life expectancy of 35 years. Predict its gestation period. So what do you do now? We've already got some work done for us. So for 35 years, what would you do with the information you're given? So remember this work right here we did? Comes into play. So if an animal has a life expectancy of 35 years, how would you predict its gestation? What would you do? Animal has a life expectancy of 35 years. How would you predict its gestation? How would you use this equation? How would you get a predicted gestation for it? How would you get a predicted gestation? What would you do? What would you do to get a predicted gestation? Thoughts? We want to predict gestation. How would we do that? Well, X predicts Y, right? So if it's 35 is the life expectancy, we take 35 and just plug it into the equation down here. Predict. Maya, I like that. Maya, 100 points. JK. Yeah, you know, you could. I wonder if I could simulate this data and then do it. Yeah, that's how we would do it, right? And that's got it right there. Yeah, the predict function would help a lot right here. And I want to point out what Maya's pointing out. Don't round, then round to 1 decimal place. There we go. Should be right-ish. We got it. Oh no, what did I do wrong? Don't tell me it was that one was wrong. It said don't round. Is it like round down? Is it? No way is this one wrong. No way. It wants you to carry every single decimal. Because I rounded to 2 decimals. Remember it was 35. We need to times that by the X. So 35 times 12.899 plus 90.8487. And it's because of this little tiny extra. So I would give that back to you if you did it. Because I rounded my equation to 2 decimals, like really that 6 100ths, not even 6 100ths, 5 100ths, 4 1,000ths, 8 10,000ths make a big difference. Like my Pearson and their rounding. So what Maya's pointing out is if you're doing this inside of R right here, what you can do a lot easier is you can have an equation like height and weight using my favorite data set, survey 10. So, we're not even got our things open. So with this, you can make a regression model like this. And with your regression model, you could predict the heights of people. So we could call data frame, data.frame. This might seem like more work, but we could literally make predictions for all the weights going from 1 to 400 pounds, or let's go more reasonable, 80 to 400 pounds. Then we could go predict using our model, and we could go here to new data equals data frame, and there's the predictions for everybody. And then what we could do here is we could make a data frame 2 where we do data.frame of predicted weight is equal to this right here, and we have weight is equal to 80 through 400, and now we have it. So that has got it. So what we've created now, data frame 2 has the weight of every individual and the predicted weight. So literally I have a lookup table now of anything I want. So or predicted height, so we can fix that. So this is the predicted height because it's the predicted Y variable. But this is what we would do in analytics to quickly do this. And you could also round those to 2 decimals by going here and go to round around this, round, and 2 decimals. So now the data frame's rounded 2 decimals. So this is the power of analytics right here, how we can do things quickly and easily with code, and like why you don't have to solve the equation. So that I love this. It's like, wow, you can just get every answer like this. And you could even put in here something like, you could just have it do a lookup, and you could watch this. We'll do one last thing. And then someone put a new question. Is it read line? Hello? There, that's what I want. Okay, cool. And, oh yeah. Enter in a weight to predict. Easy peasy lemon squeezy. So, oh, actually, watch this. Enter in a weight to predict the height for. And so we grab this right here, we go to fun, and we put nothing inside of it, and we say predict height, and we say this. That looks good right there. And then the person has to enter this in, so this will be stored as X, and we go to as dot numeric on it, and or just store it as X to begin because the code's really long. And then we take X and overwrite X with as dot numeric to turn it to numeric of X. And then we go into here, we get the predict, or we should be able to, yeah, so let's go to, no, we need to make the data frame. Data frame of weight is equal to value X. And then predict using new data. And no, that's not the predict. Where's predict function? Oh, I put it inside of here. Round to 2 decimals, predict. And we take the predict. There's the predict. We store this as prediction. And then we say cat paste your predicted height is, and then we put right here, oh, no, it's not gonna do a space right now. Is the default space? The default is a space. Prediction inches. Actually, you know what? Paste 0. Paste 0 does no spaces. So I'm gonna want it to do no spaces right here. There's a tall. See if my code works. I wrote a full function out here pretty quickly, so I'm hoping it works. So predict height. Run predict height. Enter in a weight you want to make prediction for. I weigh 190. Your predicted height is 70.27 inches tall. So all this can be done instantly. Does that make sense? So now we have a function that you can just put in your height, your weight, and it'll do it for you. So enter in a weight to predict the height for 100 pounds. There you go. And that just tells you your predicted height is this. So all we're doing is taking our knowledge of how to do these equations, and this is kind of what we do in business analytics. You could put this on the web for someone. Like if someone says, I want to predict my sales, I want to predict my customers, I want to predict this or that. You could say, oh, well, just here, input your data or input whatever you want, and here it'll just run for you. It'll do it. We can do more complex models like neural nets, support vector machine, gradient boosted models, cluster analysis, discriminant analysis. My gosh, you can do any sort of analysis you want. It's easy peasy, all of it. Fuzzy clusters, you can do fuzzy clusters. You can do gradient boosted models. What other questions are there? Here's all the models we can do. We can do Bayesian ridge regression, lasso ridge regression right there. Boosted generalized additive models. That sounds like a time series model to me. Additive and multiplicative models. Boosted tree models. Trees were taught in 201. I missed those. CART, I don't even know what CART is. Well, it's classification and regression. Well, it's almost like caret. RPART. Oh, I know what an RPART model is. That's just a tree model. Yeah, it's got complexity parameters, so that's what it is. Conditional inference tree. I have no idea what that is. No idea what that is. Diagonal discriminant analysis. Well, I already said what discriminant analysis is. That's used to do classification, as it says right there. Diagonal must be the ways in which we cut the dimensions. Never done that. Sparse discrim with tuning parameters. Shrinkage, which is going to be the learning rate. But watch this. We're going to pause the screen now. Look at the one in the middle. Flexible discriminant analysis. So we know what that is. I've never even heard of that. Once again, I like pausing the screen and just seeing what's in the middle of it. Generalized additive model using splines. Splines are so cool. I think I showed a spline in 201 a long time ago. A spline is a bendy line. I hope when I look at these, I know what the general idea of a model is. So I hope I have some idea of what it is, because then I could maybe use it. There's so many different models. There's just many models to use. There's a spline, and you can now change the lambda, which is a tuning parameter for it. And so when you go real high, you overfit. When you go real low, you underfit. And then finding the right tuning parameter requires cross-validation. These are all topics we cover in analytics, and 474 especially covers tuning parameters. But truthfully, this model right here probably, why is it showing me R squared? It should show me R squared adjusted. Yeah, so you would want a metric like R squared adjusted, which, come on, jump, put R squared adjusted in there. Because if you go to higher polynomials, they will have a better fit, but higher polynomials might overfit. And there's the high degree that's the linear fit right here, 97.1 versus the, yeah, R squared adjusted went down. So, and you're wondering, well, what does this even mean? Well, I'd have to communicate this to someone. I would say, well, if we allow the line to bend more, it does a better job. And you'd think that's a good thing, but now we can get to where we've overfit the model, as in we've taken too much information and we've only learned the data that we have. It might not generalize to new data. As in, it's like, think about this, if you had one friend, and this friend was the best, let's say, baseball player in the world, but this friend had red hair, let's say, and you're like, oh my gosh, he's the best in the world, he has red hair, people who have red hair, best baseball players ever. Well, you're right from the data you have. So here's the data we have. And you might just say, maybe I need to collect some more data, maybe I've gone too far with this data, maybe I've looked too hard into it. And that's what the 6-degree polynomial is doing. It's going too far with the data. The linear model is probably the best. And the way we'd analyze this on how far have we gone is by fairly comparing them using what is called R squared adjusted, which is the R squared adjusted for how many x's are in the model. R squared always goes up when you add x's. R squared adjusted can go down. My guess is the RMSE also went down too. It was 0.904. And now in the new model, it's higher. I meant to say go up because I meant to say it's worse. R squared going down is a bad thing. Root mean square error, which is typical miss the model makes, is going up is a bad thing, because that's more error, more miss. Any other questions? I kind of went on a 320 tangent right here, but these concepts we do in 201 apply to these bigger ideas. They apply to things that, well, like, what is a polynomial model? Well, it's just a model that allows the line to bend more. So we are verging into these new ideas. Might do chapter 8 homework, see if we can do the full homework here. That way people can come back, watch the full homework. But anytime I'm going on and on about stuff, just drop a question. I love stats. That's my problem, is I love stats. Stats is a lot of fun, and it answers questions. You just go to the data and say, well, what's the data say? And then the problem is sometimes you have to give it an interpretation. Sometimes you be like, well, the data is just numbers, and then what does that mean? What is the data? What do we think from the data now? Okay, let's do chapter 8 homework. Hey, Amy. What have we covered so far? Here's what we covered. We're about to do the chapter 8 homework. So here it is, what's been covered right here. There is and I'll save it in the video. So if you reload the video now, it should be there in the video. So check that out. There's what's in the video right there. You're welcome, Amy. We're gonna do the chapter 8 homework. Let's do it. Okay. A concert production company examined its records. The manager made the following scatter plots. The company placed it in 2 venues, a smaller one and a larger one. And with the larger auditorium with the red X's. So here's the larger one. And you can kind of see what's going on with the data. You've got a linear relationship, and the blue one has a smaller range for talent cost. So the scatter plots show a definitely positive. So there's one outlier. Is there an outlier? I don't know. Shows a positive linear relationship. There are no outliers. We have such an easy way to answer if there's outliers. I don't think there is outliers, but the reason I groan sometimes is because I can always look for outliers with an influence plot. It's very easy to analyze, are there outliers? And the answer here is yes, there are outliers. There are very quick mathematical ways, and on the test we make them rather obvious. So looking at the original visualization here, if we asked you on this one, are there outliers? Yes, right down there. And the quick way, once again, is if you can make what we call diagnostic plots, you can quickly tell, and we even put X's on them to let you know. Those are highly influential points, and they're also large outliers via their deleted student eyes or residuals. So once again, on the test, and it's mad at me, it's saying there is one outlier. Let's look again and see if we see it. I think they're talking about this one. Yeah, if you go through the data, it's like, kinda, I always get mad at a subjective question. It's multiple guess, so you can get it right no matter what. If you go through the data without that point, it looks something like this. The point kind of has a big outlier. Kind of iffy. It's definitely positive relationship, so we can't get that wrong. So there's one outlier. Sure. Very similar. They both have positive relationships. An increase of venue with increased venue with talent cost. Oh, you see they put the cause word there? Do not say cause. That eliminates those answers immediately. Cause is a word we don't use in statistics. Correlation is not causation, nor is an association correlation. How are they different? The smaller venue had a smaller range of the X's. So if you look again at it, the blue dots, the smaller venue has a smaller range of the X's, where the red dots have a larger range of the X's. That's the first thing that comes to my mind. This larger venue has greater variability. It'd be easier to predict the greater variability. The larger venue has greater variability. What? Oh, they're talking about in the Y also. I need to slow down a little bit. Let me point out what they're talking about, because I went too advanced on this. There's a lot of concepts that are at play right here. And when they're talking about variability, they're actually talking about the variability in the Y, which is going to decrease the R squared because there's a greater spread to the data, where the blue has a tighter relationship, which is a higher R squared. What I was thinking is variability in the X, which relates to the standard error of the slope, and the standard error of the slope is more certain when the X has a greater span to it. So there is more variability on the X for the red ones, and the problem is, and what they're going for is an R squared idea, or a root mean square error, typical size of the residual, and they're saying that this is more spread out, and more spread out means higher variability in the Y, and means lower R squared. Now, when you think about R squared, remember it is correlation squared. It's not correlation. So since there's more spread to the data, that's a lower correlation. And with there being a lower correlation, there's an R squared that's lower, making it harder to understand the variability. We'd have a better understanding of the variability in the blue one because it's tighter, and the variability in the red one is more spread out and harder to understand. So good job. And I need to slow down a little bit here. Slow down a little bit. Let's do the next one, and we're slowing down. Noting a recent study predicting the increase of cell phone costs, a friend remarks that by the time he's a grandfather, no one will be able to afford a cell phone. What is he doing? Really good quick concept here that we talked about earlier, and we have a graphic up for. He is taking his current understanding and extrapolating. This is a concept we cover in 320. When you go outside the X bounds, or sometimes where you have no data within your model, you are extrapolating to say the linear model would hold. So the question to know if you're extrapolating is, do you have X's? Does he know in the year 2080 what cell phone prices will be? No, he's extrapolating from current model. What actually happens is the model spreads out mathematically, and we wouldn't have very little certainty. So he is extrapolating. He would have no idea at that point that far in the future. It's very uncertain. He could make a prediction using the model, but he's probably not going to have a good idea. Very, very uncertain idea. Using data from 20 compact cars, a consumer group develops a model that predicts the stopping time for a vehicle by using its weight. You consider using this model to predict the stopping time of your large SUV. Now notice they're using a compact car. You drive an SUV. So the data you're using is they're using the weight of a compact car, which is a lot lighter than yours, versus your SUV, which is probably a lot heavier. This is not advisable. What we should do is we should look up extrapolation right here, which it won't let me even search this. No, because the answer is going to be we are extrapolating. So this is not advisable. The model predicts the stopping time for compact cars. The SUV is not a compact car, so the model's predictions are not reliable, and it didn't even say the word extrapolation. No wonder it didn't blink or blinked for me, because it is saying to you, you are extrapolating beyond the weight of the car because you don't know around your points what the data should look like. Extrapolation is going outside the bounds of the x's and making predictions of y where your model wouldn't have an understanding. So here we are with an equation. Now, once you get an equation, immediately go in and mark it. So notation is one of the most important things to know and often underlooked. We basically have it right here. So we've got, let me do a new sheet instead, the equation in its filled out form, but now you need to go in and mark the notation. The equation is y hat, notation is fundamental, Amy knows right there, b0 plus b1x right there. So there is the equation right there where the intercept is b0. When x is equal to 0, we expect y to equal b0. The slope, b1, for each one unit increase in x, we expect y to increase or decrease by b1 on average. And the x variable right there, and the predicted y variable predicting revenue. So now you go back, and we can look at the data. You can see the positive relationship. You'd be extrapolating down here. You'd be extrapolating beyond here. I think they do an extrapolation on this question. So they want to predict for 10,000 seats. Yeah, that's an extrapolation. So 10,000 is well beyond the model. Simply plug 10,000 into ticket sales, and then times by the slope coefficient, add to it. Sure, we'll do add negative for 31000 minus 714. Oh my gosh. Was that right? Minus. There we go. And type in integer or decimal. I think we're good. Good. Once again, just plug 10,000 in for the value of x. That's how we use equations to make predictions. Is if it says predict for 10,000, all you do right here is take the value of x and simply plug in 10,000 into x right there and make your prediction for predicted revenue. So would it be, this is just a ridiculous extrapolation. Where's the extrapolation? I didn't click it. That is an insane extrapolation right there. Insane. The correlation between temperature and number of skinned knees on a playground. Does this tell us that warm weather causes? No. So any no, and we would just say warm weather will cause less children. No. So I don't like how they say it will cause this. It's kind of true, but we don't like the cause word. It's just we would say there's an association. But so the way they word that is we never like the cause word in statistics. It's just we have evidence of an association or correlation, but we can't say things cause things. A variable that is not part of a model that affects the variables in the model is called a lurking variable. Make sure to know, and I think they have response and explanatory as the other answers. Response is the y, explanatory is the x, explanatory. Lurking is a variable outside the model. Classic example of this is going to be when you have your data, such as one of the famous examples we use a lot of times are shark attacks. And ice cream sales. So you might say, does shark attacks cause ice cream sales? Or is it ice cream sales that cause and explain shark attacks? In truth, there's a z variable. So no matter how you think about this as your x or your y predicting ice cream sales from shark attacks, there is a z variable, which is probably weather, which explains them both. So when you write your equation, there could be something outside your equation, another variable called a z variable sometimes, I like to call it that, that actually explains it. So since it's not in your model, like if you look at this equation, anything you can name, like, think about this, what would explain the revenue? Also would be artist. What artist is going to make more with 10,000 ticket sales? Taylor Swift, or I'm trying to think who else. We'll say 1,000 ticket sales, or let's say 100 ticket sales. You go to an event with 100 ticket sales and they want to know the revenue from it. And it's going to be Taylor Swift or a local artist. Sorry, local artist, go see your local artist. Well, ticket sales do explain revenue from an event, but also the artist would be another variable. You say, well, how in the world did they make $1 million on this event with only 100 ticket sales? And they said every ticket was $10,000. You're like, what? It was a Taylor Swift 2-hour meet and greet. Taylor Swift and 100 fans. So Yeah, I guess I'm trying to think. Or a 6-hour event. You get to like have breakfast and lunch with Taylor Swift, 100 fans, and they cycle out who's kind of at the table with Taylor Swift every hour. So price sounds, I know, right? For $10,000, like Taylor Swift could probably do that. Like 100 fans, $10,000, and they even like pay for your ticket there. They pay for your plane ticket. So it's like travel included. They set up your travel. It's all expense paid. Hotel is paid. $10,000, and Taylor Swift wouldn't probably make $1 million then. She probably, I mean, think about that one. You can, I mean, she's doing fine, but man, that'd be crazy if like you're like, you know, I could just do one event one day, have breakfast and lunch with people, and then you know, clear probably would make like 400,000. The event organizers were probably like, the event's going to cost a bit to run. Need security there, need all these things, need the venue, security, food's going to be less, but I mean, you want to get some good food. Like, if you're running $1 million event with food for 100 people, you could drop $10,000 on food. I know that sounds insane, but we're talking $1 million event. I don't know. I've never priced these things. I'm just like, I'll go all out. We're getting filet mignon for everybody. Well then, oh no, filet mignon per person might be $50 a person. So I don't know. I'm not planning this event. And then local artist does the same thing and says, I'm going to make a ton of money. Good to see you there, Jennifer. So we just did the full thing, and that'd be the lurking variable, because like ticket sales don't fully explain the revenue you make from an event. Artist is another variable that we haven't considered here. So you might say, well, why did this event make so much? It'd be a lurking variable that's outside the model that helps explain it. So we call those lurking variables right there. You can think about a confounding variable too. Those are usually when variables are contained within other variables, like high selling events are usually contained within big artists. Like if we were to look at, was this a high selling event? Was this a big name artist? Those two are confounded because high selling events are going to be contained within, like you have a high selling event because someone's big name artist, a big artist has high selling events. It's very hard to untangle those. Like you'd have to have instances of low artists having high selling events or big artists not having high selling events, and then you could figure out the impact of those variables. They're just blended together. So confounding variables, lurking variables, response variables, explanatory variables, predictor variables, independent variables, all the variables. What should we do? We still have 25 minutes. We did all of chapter 8 homework. For the but when you have time, what's the difference between marginal and conditionals? Oh, I like that. Hey, I graduated in May. I've been trying to figure out how to fix my visuals in Power BI. A real job. One of you trying to show you live. Hey, Mary Bell. I forgot about Z-scores. No, that's all right. 100 points, Mary Bell. Let's talk about some conditions. And great job on the Power BI. We do that in our capstone classes. We use Power BI, Microsoft product right there. Really great product. And Mary Beth, give some advice for students right there. My biggest thing is keep getting those skills. Companies want you to be able to visualize, interpret data, tell stories with data. And like this graphic right here probably means nothing to anybody. I probably wouldn't show it to a company because they'd be like, what's going on with this? And I'd be like, well, it's letting me analyze for outliers. And I see some outliers. And that's what I'm learning from it. So you have to know what you're looking at and what it means. And they have to build something a lot of times with Power BI that is manageable for non-technical people so they can get the analysis like that. Because we can make the analysis, but the real power of analytics is making analysis manageable and understandable for people who don't do analysis on a daily basis. That's the real power. And Mary Beth, we'll throw another 100 points. Thank you for swinging by and saying, hey, I just love people swinging back by and saying, here's what I'm doing, which really makes me realize we need even more Power BI. This just solved my problem. I had insane outliers. What? No way! Yeah. Exactly. So you probably need to figure out the lurking variables that cause out. Like it probably is due to some lurking variables. Maybe it's like a special product people are ordering. Like there could be a lurking variable that like if you're looking at, I'm looking at how long it takes to process orders. So your Y variable is time to process order. You've got some X's, and then there might be something lurking, like another variable in play here. So maybe see if controlling for more variables, a Z variable will help with that. Maybe look at like a cluster analysis. If you know cluster analysis, we do that in BS 474. See if there's some sort of trend in the longer orders. Like maybe they're coming from a certain region, maybe they're for certain products, maybe they're for certain consumers, maybe they take certain routes. Like what is the explanatory variable? So Mary Beth, really good work out here. And this is what you do at a job is you're like, why do these orders take so long? Because that's what the customer wants to know. And so then you have to figure out the variation, you have to adapt the variation, you have to control for it and solve the problem. So I like that. Yeah, we had late shipments, max 450 days, but our goal for average was Well, I will say this: COVID totally changed the process. COVID totally has, one of those outliers might be start of COVID or something like that, and then you could maybe throw it away because people know, barring crazy world events, usually we don't see something, crazy. And let's go. Good. Thank you so much, Z. We'll do your question right here. Marginal conditionals. What's the difference between marginal conditionals? Why different X? Let's do that. And so, Mary Beth, really awesome. That's stats right there for you. That is the application of business analytics right there. Okay, marginal and conditional distributions. So when we talk about a marginal and a conditional distribution, if you're in 201, you've seen this. So we're going to load up survey 10. We've already done that. Now let's load up survey 11. They have churchgoer and stuff. This is a fun one. So let me go attach. And survey 11. Thank you so much, Mary Beth, right there. I really appreciate that. Let's look at, I'm gonna do smoker. Does smoker explain how people attract someone? That's the X variable. Does smoker explain how people attract people, like what they use to attract somebody? It's almost statistically significant. Ooh, those. It's not statistically significant, but we'll still analyze it. Okay. So when we look at this right here, we need to know all the output, every bit of the output, everything in here. First off, let's start from the beginning. There were 628 complete cases analyzed. That's just the number of rows in the data. If you go over here and look at the data for the data frame, there are 628 and they were all complete. That's why we're able to analyze it. That's all that means. 628 people were analyzed. In here, we see the contingency table with the marginal displays. There's our marginal display there, and the other marginal displays on the side. Only 63 smokers. A marginal display is a display of one variable in a bivariate display. The marginal displays are in the margins of a contingency table or the margins of a mosaic plot, which is the visualization of the contingency table. So when you go in here and you look at a marginal display, the marginal display of weapon to attract mate is over here in the mosaic plot, showing for everybody what do they use to attract the mate. Versus over here, it's here on the contingency table showing the same numbers. Notice how most people use humor, and most people use humor. That's the same data, just as numeric values. And then we look at the marginal display of do you smoke? Really? Can't erase that? No, we're not going to erase that. Marginal display of do you smoke is right here. Most people do not smoke, only 63 smoke. So the 63 is the width of this right here, which 63 is right there, the marginal display of smoking, not smoking. Conditional display is found by looking within, which means given somebody is a smoker, what is the weapon of attraction they use? So you'd look within here, and given somebody is a smoker is going to be this data right here. Only 10 of the 63 use other, and that is this right here. It's very hard to mark just that, but you would look within it. So a conditional display is for a certain level of an X, looking within it. If you look at conditional on given somebody is not a smoker, that would be right here. And so the 100 that use other is right here. And this is the conditional not smoker right there. And we can ask important questions like what percent of people, and check out yesterday's Kahoot, a lot of work on that. We did some expected values right there from it. We can look at the next thing too. Look at more at the output on the screen. The next part of the output is the table of expected counts, which actually does row total times column total over grand total. Remember, the equation is row total times column total over grand total to get any of these values. So always try to solve for these values if you see them. Put examples on your worksheet. So if you wanted to solve for the expected value of right here, which would be this times this over this. So 110 times 63 over 628. We solve that out and we'll prove it by going here. This is how many we would expect by random chance, given there is no association. It is actually doing the multiplication rule in Stat 201, because when you times together two probabilities, you get the expected given, or you get the rule is independence, excuse me. When you multiply two probabilities, the assumption or the rule that you are following is that the two things tell you the independent probability of them both happening, and thus 11.03, which has been rounded here to 11 right here in this output. Now notice how this is other and yes, and that is the expected or predicted given no association. Here's the marginals and conditionals. So this is the marginal, which 46% of people use humor, which is that. Intelligence for everybody is 14%, where notice how given somebody is a smoker, it's higher at 22%. Once again, to find the 22%, we could go back to the original data and notice how 14 people use intelligence out of the smokers, which is that right there. So we know how that number is calculated. Given, we go here and say, given someone is a smoker, what's the probability, 14 out of 63, that they use intelligence to attract a mate? Down here, we get the permutation procedure, which the discrepancy would tell us this is a 2 by 4. So we divide that by 3. The discrepancies we see in this data are about 3.25 times higher, 3.4-ish. Divide that by 3. 3.46 times higher than we would have expected by random chance given no association. And what we did is we took the degrees of freedom, and the degrees of freedom need to be, this is a 2 by 4, so you delete one row, delete one column, 3 degrees of freedom. And with 3 degrees of freedom, we divide the discrepancy by the degrees of freedom. So we got that there's the value, 1.46, and that tells us about how many times larger this discrepancy is than we would have expected by random chance. An expected discrepancy is a discrepancy when we do this math here of 1, because then we saw about what we expected. The discrepancy is the observed over the expected. So if the discrepancy is about 1, then when you do the math here, you're seeing what you would expect. Like imagine you order a steak and you expect it to cost $20 and it costs $20. There is no discrepancy. So a 1 means you observe it costing $20 and you expect it costing $20. Thus, the discrepancy is 1, and it's the same as what you expected. And then it would have a higher p-value. In that instance, a p-value about 0.5, because the probability it's as large or larger than what you would expect is about 50%. It could be smaller half the time, it could be larger half the time. If it was 4 by 3, yep, that would give 6 degrees of freedom, correct. If it's a 4 by 3, so you hold up your hand right here and then you delete one number and you times, and that would get you the degrees of freedom to divide that number by down there to figure out about how many times larger is the discrepancy than what we expected via random chance. Does that all make sense right there? We did a lot, and then the p-value right there tells us that what we see is likely by random chance. The differences between these, as in the differences between the conditional distributions and the marginal. So here's a conditional and marginal, and the differences we see there are likely by random chance. And then also we are confident, because 0.05 is not included in the interval, that the discrepancies we are seeing here are probably likely due to random chance, because it's a high p-value and we do not think it's possibly below 0.05. This is the visualization of the contingency table. This is the visualization of the permutation procedure, showing us most permutations are very small by random chance. There is 21% of the data at or above our line right here. So if you went to the line, let me screenshot that. Yeah. So if you go to the line, 21% of the random permutations, so that's 21%, are as large or larger than ours. And this is our discrepancy value right here, calculated to be, that is 4.39. And you can see right there where it hits. So 4.39 is where it hits, and 21% of the random permutations are as large or larger than ours. Random permutations are created by random chance, as in we create a random X and random Y using the data. We just permutate them, like the numbers 58921 could be permutated to 92581. Numbers 1 through 10 could be permutated to 921, 3, 5, 6, 7, 4, 3. I think that's the only one I missed. And 10. Technically, the numbers 1 through 10 could be permutated to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So technically, permutations can reproduce the data, but that's unlikely by random chance. It'd be probability of 1/10 times 9/10 times 8/10, because they have to go in order. And so very unlikely probability to reproduce that same data. And for larger data sets, is even less likely. So that's why you could get discrepancies as large as yours. Yours is possible by random chance. always possible, but is it probable is decided by the p-value. And this is possible by random chance. So we think any relationship we see here is by random chance. Let's do another quick variable. I always love these data sets. So let's see, smokers and alcohol. We'll just go with all that. And yeah, smokers prefer their liquor and beer. And notice the big change right here is really on none. So once again, this is real data, which is the fun of analyzing it. And we do see an association between are you a smoker and what's your favorite alcohol, because the big, really where a lot of the data went from was the none group. If you look up here, became more part of the liquor and beer. Wine really didn't have much of a change. It did increase, but where we saw the decrease was in none, where smokers, only about 5% of them do not drink, and non-smokers, 23% of them don't drink. We saw the biggest gain, I would say, in beer, because beer jumped from 26 to 35, which is an increase of 9%-ish. And then right here, we see an increase of 8%. But comparatively, 25 to 35, 26, we'll round it up. 26 to 35 is larger than 39 to 48. They're about the same, but comparatively, the beer got a bigger jump. It's just, it looks like the red is higher because the red also starts out higher. So pretty cool analysis and pretty cool fun things you can do pretty quickly. Might not find out the most interesting things. Let's look at, this one has the churchgoer, doesn't it? Not a churchgoer. Churchgoer. Alcohol and churchgoer. Yeah, this is a craziest. This is the strongest one we've seen, because people, or we could say, let's do favorite alcohol explaining or churchgoer explaining favorite alcohol. And now you can see it right here where the none group takes a big jump, and then people who go to church would be most likely to like. Wine just held out. Wine actually got higher, which is interesting because everything lost footing except for wine, where people who go to church, wine is about 13% and it was about 11%. So wine was the only one that gained. I mean, think wine is the alcohol maybe during a church service if you're having communion or something. It kind of makes sense, but once again, that's us giving our interpretation. Relationship status. Let's see here at the relationship status and going to church. I just love analyzing data. Oh, there is something here. It's smaller. People go to church. Ooh, wait a minute. Look at this. Single, right there. There it is. But doesn't mean if you go to church you can be single. It's just there's an association. Number of drinks per week. Favorite alcohol. Night in jail. I bet you night in jail. Let's go look at this. And then passed. It did it. Just not a lot of nights in jail. It's a good thing. Did you see the last Harry Potter movie? Ooh, is interesting because Harry Potter, back in the day, there used to be some conflict. All the relationship here is by random chance. And so you'd be like, oh, there's a difference. People who go to church are less likely to say Harry Potter. Well, this is about as small as a discrepancy as we can see. I just love analyzing data because it's cool. Sometimes you find something you don't expect. And you never know what you're going to see with data. And this is fun data, like political beliefs right here. Go to political beliefs, and whoa, that's the strongest one we've seen. So liberals go to church, conservatives don't go to church, but there's a strong association here between going to church and being more conservative. Which is something we generally have seen in our society. It's just sometimes you get data that confirms what you believe, and you can see to what extent, and this is the strongest association we've seen. But remember, trends in data don't imply that everyone follows the trend. It's just that what we see right here is that given someone goes to church, it's more likely they're conservative. It doesn't mean they are, it's just a higher probability. But do remember that individuals are individuals and never make assumptions, because we always try to find out first. Don't be like, oh, there's a trend in this data, I bet you follow the trend. No, talk to people, get to know them. That's my advice right here. Till then, bye everyone, bye.